And in problem number 3, there's not much that we need to do other than playing with this code. Okay, so the actual problem is not that complicated. It's based on something that I showed in the lecture, so you just need to mimic what I demonstrated in lecture. But here I'm just going to showcase some of the programs that we have from our main textbook or supplementary textbook. So the first one is called FP2 IEEE.m. So this is floating point to IEEE. Okay, so this is coming from our main textbook, Learning MATLAB, written by Professor Overman. And if you type help, by the way, these code will be, I will make it accessible to you. So you should download this onto your working directory. As you can see in this current directory, I downloaded these two programs. Okay. So when you type help function, it tells you what it does, and it essentially converts floating point numbers to IEEE specification. Okay, so as an example, let's do floating point to IEEE, and let's convert one. Okay, so when I run this, and maybe I should make it larger. So sign is equal to 1. Okay, it means it's a positive number, and this is the sign bit, if you like. And this is bit notation. Okay, and yeah, so we know that we use 64 bits. Some of them are used to represent exponent. Okay, and some of them are used to represent mantisas. Okay, but yeah, these are 64 bits. Okay, binary bits, okay, zeros and ones. It may not make too much sense. In such a case, you can look at them down here. So the very first one is sign bit, and when sign bit is equal to 0, it is positive. And these are exponents, okay? And you should turn this into, these are in binary, so you should turn this into decimal, and then you have to offset by subtracting 1022. And then this is our mantissa, okay? But in my personal opinion, what's most useful is this line right here. So 1 in scientific notation is written as 1.0 times 2 to the power of 0, okay? And here we have 52 places right here, okay? So all of these places after the point are all equal to 0. Okay, so when you do 2, you'll still have 1, but you now have 2 to the power of 1. Okay, 1 times 2 to the power of 1 is equal to 2, and another power up to 4. Okay, so 1 and clean digits after the point. Okay, multiply by 2 to the power of 3. Okay, so what if a number is not a decimal, number is not a power of 2? Okay, for instance, if you look at 3, you get 1.1 times 2 to the power of 1. Okay, so in binary, so this is 1, 1. Okay, so 1 here means 1, and 1 there means 1 times 2 to the power of 1. Okay, so that's 3. Let's say 7. Okay, let's represent 7. 7 is equal to 1 plus 2 plus 4. Okay, so in binary, it is 111 base 2, but written in scientific notation, you write it as 1.11 times 2 to the power of 2. Okay, power of 2 has the effect of moving this point to the right by 2 positions. Okay, so this is nice, and we can use this to inspect how some of the predefined variables are represented. For instance, we have this number called real mean. And for real mean, we once again has a very clean number here, 1.0. and we multiply this by negative 2 to the power of negative 1022. Okay, so keep in mind that 1022 is the offset. Okay, we've been talking about in the exponent, and when you do real max, okay, this is the largest exponent that you can obtain. Okay, and not only the exponent is as large as it can get, but we are filling all the mantissas with ones. Okay, so this is as large as we can get, and if you were to say try to multiply this by 2, there's no more place and the program is going to complain. And how about EPS? EPS is the gap between 1 and the next floating point number, and this is called machine epsilon. And you see that 1 EPS is equal to 2 to the power of negative 52. Okay, so when I do 1 plus EPS, you'll see that the effect of EPS appears over here. Okay, so this is the smallest possible contribution that we can make when I have 1 point something with 2 to the power of 1. Okay, so this is 1 is represented as 1 times 2 to the power of 0. And the next number that I can possibly represent will have 1 over there. So I click the very last digit by adding EPS. Okay, so this is 2 to the power of negative 52. And when I do 2 times EPS, okay, it's right there. Do 3, then the last 2 digits over here is going to be 1, as we can see, and so on and so forth. Okay, so you know that when you do, say, 1 plus half of EPS, there's no way for this number to make any meaningful contribution to this. Okay, so it's halfway, and the convention is that the number halfway in between two floating point numbers will be rounded down. Okay, so that's what we get. But if you pass that halfway mark, it will get rounded to 1 plus EPS. Okay, so it's rounding up behavior. Likewise, 2 plus 2 times EPS. Okay, so let me get up this first. When you have 2, you have 1 point and all zeros with this exponent, 2 times 1. And in order to have an effect on the very last digit, 1 EPS is not enough. You need to have 2 EPS. Okay, and the next one is going to be 4 EPS, and then the next one is going to be 6 EPS, because that's 3 times 2. Okay, and so on and so forth. So we know that the gap between two neighboring floating point numbers changes depending on where you are. Okay, and there's this another program that I wanted to introduce to you, which is called Float GUI. And I think let me run this from here. Float GUI. Okay, so it opens a new program. Okay, so this is graphic user interface illustrating floating point numbers, and this is written by Clive Muller, who invented MATLAB. Okay, so here is a very simplified snapshot of the floating point numbers, their distribution, when the smallest exponent is -2 and the largest exponent is +2, and the mantissas, you only get 3 digits for mantissas. Okay, so between 1 and 2, okay, so in between two consecutive powers of 2, you get 2 to the power of 3 floating point numbers. There are 8 of them: 1, 2, 3, 4, 5, 6, 7, 8, and these are spaced out by 2 to the power of -3, okay, which is 1/8. Okay, So that's the gap from 1 to 2. And moving on, 2 is 2 to the power of 1, and the next power is 2 to the power of 2, 4. Okay, so between 2 and 4, this gap has been doubled. Okay, so from here to here is a quarter, and you have 8 quarters. So that's the gap of 2. And from 4 to the next power, which is equal to 8, you have to double the previous gap once again. So from quarter to halves, half, you get 8 of them. So this is 8 minus 1/2, and the last one is equal to 8, okay, with the gap 1/2. When you go to the left of 1, excuse me, the gap gets half. Okay, so from here to here, this gap with red is EPS, machine epsilon, and the gap between 1/2, which is 2 to the power of -1, to 1, which is 2 to the power of 0, is half of 1/8, which is 1/16. This is 1/32, and 1/64, and so on. Okay, and as you can play with this. So if the minimum exponent is -5, then the smallest number that it can represent becomes 2 to the -5, or 1/32. And by increasing maximum exponent to say 3, you can represent up to 2 to the power of 3, 4, 2 to the power of 4, well, minus appropriate EPS. But yeah, so that's what this program is doing. Okay, so if you're interested, please play with it. All right, let's move on to the next problem.